Okay, we will go ahead and get started here. I'm Randy Anderson on behalf of the leadership group here at Science, Scripture, and Reason. We welcome you to our April 2026 meeting, and we are really delighted to have Dr. Michael Strauss with us this evening. Um, for those of you who don't know him, Dr. Strauss did a Bachelor of Science degree at Biola, I understand, because he really wanted to study both science and theology, and a PhD at the University of California, Los Angeles, and is a David Ross Boyd Emeritus Professor of Physics at the University of Oklahoma at Norman. He was most recently conducting research in experimental particle physics at CERN laboratory in Geneva, Switzerland, studying the fundamental particles and forces in the universe. Earlier research at Fermi National Laboratory near Chicago and Stanford Linear Accelerator Centers. Dr. Strauss has worked as well, and he has amazingly over 1,000 papers published in peer-reviewed journals. I can't imagine how much work that was, but years and years. It's absolutely amazing and shows his expertise and status in the field. Um, he's spoken at on the intersection of science and Christianity at universities, schools, and churches throughout the world, and is the author of the book "The
I'm
Creator
not able to bring
Revealed:
it over.
A
I
Physicist
can't. I
Examines the Big
can't. I
Bang
have
and the
no.
Bible." Um,
So Dave said this is
somebody
connected to
needs
the blue.
muted. Thank you. And beyond that, he is one of the general editors of Zondervan's Dictionary of Christianity and Science, and he is the co-recipient of 2024 Texas A&M Trotter Prize for his work in illuminating the mechanics and wonder of nature, particularly relating to the connection between science and religion. So we are extremely delighted to have Mike Strauss with us this evening, and he's going to take us on a journey from the biggest in the universe all the way down to the smallest, and show us how that reflects God's design and glory. So, Mike, thank you for coming, and I'm going to turn it over to you.
All right. Thank you for inviting me. It's great to see all you on Zoom. I hope you can hear and see me. Let me share my slides.
And there's a presenter.
All right.
Essentially, the snake one. Oh, no.
Yeah, so people should mute, please.
Well, and I don't have good speak. These are not good speakers.
All
So
right.
it's not going to those.
So can you mute people from the room? That might be good. All right. All right. So thank you again for inviting me. As was said in the introduction, I'm originally from California. I spent 23 years of my life in California. My mom still lives in Escondido, Southern California. As was said, my undergraduate degree was from Biola University in the Los Angeles area, and my PhD was from UCLA, also, of course, in the Los Angeles area. I spent a large fraction of my time up in the San Francisco area. I did graduate work at UCLA, but my research was actually at the Stanford Linear Accelerator Center. So I lived there for many years. I eventually did a postdoc there. I met my wife there. Both my kids were born there, one at Stanford Hospital, one at Santa Clara Hospital. So California is home when I go back to Los Angeles and get stopped completely on the freeway because traffic is totally stopped on the freeway. I feel like I'm right back home. So, that's something we don't have too often in Oklahoma is completely stopped traffic on the freeway. But nevertheless, I've been at the University of Oklahoma now for over 30 years. Oklahoma is a research university. So my primary job is research, and my secondary job is teaching. My research is done at CERN currently, which is a laboratory on the border of Switzerland and France, and I'm a member of the Atlas detector. I'll talk a little bit more about that as we go on through the talk tonight. My research is in experimental particle physics, which deals with studying the smallest particles of the universe. This is what we know about that. Everything is made of atoms. This will be on the quiz at the end, so make sure you take really good notes. Everything's made of atoms. The atoms have electrons kind of in orbiting around the nucleus, but the center of the atom is the nucleus. The nucleus is made of neutrons and neutrons and protons are made of quarks. I spent the first 20 years or so of my career as a particle physicist studying quarks. I've spent the last 15 years or so studying a particle that was discovered in 2012 called the Higgs boson. Here's a picture of the CERN laboratory. It's on the border of Switzerland and France. Again, I'll talk a little bit more about what we do at CERN as we go on in the talk later on. Um, Not only am I a scientist, but I am a Christian, and people often ask, can you be a scientist and a Christian? Aren't those two things incompatible? Doesn't science have to do with objective, factual reality, and Christianity have to do with subjective feelings or beliefs? Do you have to compartmentalize your life and live differently as a Christian than as a scientist? And of course, the answer to all those questions is that science and scripture should mesh completely. We believe science is just the study of God's creation. The Bible is God's word, so they have a common author and they should reveal a common truth. And this is, of course, what I have found as I have studied science and scripture, that they indeed share a common truth and a common author. Now, this in some sense shouldn't be surprising because the Bible itself declares that when we look at nature, we should see God's hand in his work. Psalm 19:1 is perhaps one of the most famous verses on this subject, which says, "The heavens declare the glory of God, and the skies proclaim the work of his hands." And, I'm sure that we all have looked on a beautiful sunset or beautiful mountains or something and felt this awe, this sense that there is a God out there and this beauty that he's created. I have a friend who is an artist. In fact, one of his paintings actually is displayed in the Oklahoma State Capitol building. So he's actually a pretty good artist. And he says when you look at a piece of art, you see the soul of the artist. So, God's work, their creation is God's piece of art. And so when we look at it, we should see the soul of the artist. When I was an undergraduate at Biola, one of the classes I did not want to take, but I had to because it was a liberal arts college with a liberal arts education, was an introduction to art class. So I waited till my senior year. I took an introduction to art class with a bunch of freshmen in the class. And it turned out actually to be one of my favorite classes. And the reason was because I learned things that I did not know before. I learned things that artists do in an attempt to actually force you to look at certain points of the picture, like the way they might have light shining through a window, or the way they might have someone looking at something else. So that will draw your eye to the other thing. And what I learned is that when you are an expert in art, you actually see things in the painting, in the picture, that the non-expert doesn't see. And so if we want to look at a piece of art and see the soul of the artist, the non-expert sees the art in a certain way and sees maybe the beauty of the art, but the expert sees details and intricacies that the non-expert doesn't see. And so what I kind of want to do today is, as a particle physicist, I look at God's piece of art and I may see intricacies or details that the non-expert might not see. And so we're going to talk about some of those things as we talk about from the big to the small. And overriding this all, I think, is like personal applications. I mean, I have questions for God. Maybe I can learn something about the answer to those questions by looking at God's creation, by looking at the soul of the artist. I'm sure I'm not the only one who has questions for God. I often wonder why God does the things he does and the way he does. Why does he bring certain circumstances into my life? If I was God, I'm not sure I would do things the way he does. I have questions like, does God really know what's going on? What's up? It doesn't seem fair. I don't get it. And I wonder if by looking at his piece of art, we might get some of these kinds of questions answered. Now, I'm not the first person to have questions for God. This is a artist depiction of the prophet Isaiah, who lived about 700 BC. Um, and at that time, the nation of Israel was divided into two parts. There was the northern kingdom of Israel and the southern kingdom of Judah. And the northern kingdom of Israel had been attacked by Assyria and had basically been taken up into captivity, the people. And the southern kingdom of Judah was also being attacked and was declining politically and economically. And the people had questions for God. They felt that God had abandoned them, that he had forsaken them, and they didn't understand what God was doing. In Isaiah chapter 40, the people say to God that the justice due them escapes the notice of my God. In other words, they are crying out to God. They feel like he should be serving them justice, and he's not. They feel that the circumstances in their lives demonstrates injustice that they are experiencing and that God doesn't care. And so they have the same kinds of questions for God that I sometimes have. And in the midst of these questions, God gave them a message through the prophet Isaiah. And it's a partial answer to some of the questions that we ask of God. It's recorded in Isaiah 55. And what God says through Isaiah is, my thoughts are not your thoughts, neither are your ways my ways, declares the Lord. As the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts than your thoughts. The message of this word from God to Isaiah is that maybe we shouldn't be surprised when we don't get what God is doing, when we don't understand his actions or why he does things the way he does. His ways are different than our ways. His thoughts are different than our thoughts. In fact, he gives a illustration here. He says, as the heavens are higher than the earth, so are my ways higher than your ways. That is how different God is than us. It's as the heavens are higher than the earth. And that gets me thinking, as a physicist or as a scientist, well, if God's ways are as different than my ways, as the heavens are higher than the earth, and his thoughts are as different than my thoughts, as the heavens are higher than the earth, well, how big is that? How high are the heavens above the earth? So I decided, let's take a journey and see how high the heavens are above the earth. And maybe that gives me an answer as to why God does things differently in my life than the way I think he should. Well, of course, the closest object to the earth in the heavens is the moon. It's about 240,000 miles away. That would be like traveling around the earth itself about 10 times. In 1968, we first took a journey to the moon in the Apollo 8 mission. So the Saturn V, which at the time was the most powerful rocket ship ever built, fired off in 1968. It took 3 days, a little over 3 days to get to the moon. And on Christmas Eve 1968, as Apollo 8 was rounding the moon, it took this famous picture of the Earth, the first picture of what was called Earthrise. And it's interesting, as Apollo 8 rounded the moon, the astronauts actually read the creation story from Genesis 1. And this had significance. People forget this, but back in 1968, we were in a Cold War with the Soviet Union. And the Soviet Union were the first to send astronauts into space. Yuri Gagarin was the first astronaut. And when he went into space, Premier Khrushchev, the premier of the Soviet Union, said that Yuri Gagarin went into space and he didn't see God, because the Soviet Union was a devout atheistic society with a mission to stamp out all religion. So it's extremely significant politically, as well as spiritually when the Apollo 8 astronauts rounded the moon and read from Genesis 1. They were basically saying that we as a nation believe in God where the Soviet Union didn't. And so that's one significance of this picture, but there's another significance. To me, when I face challenges and problems and difficulties in my life, they seem really, really big to me, overwhelming at times. But from this vantage point, none of my problems look very big. In fact, my whole life looks pretty small when we look at it from this vantage point. It's kind of cool, right? Because this picture was taken in 1968, and just this month, we finally did the same thing. We sent Artemis 2, now the most powerful rocket ever built, around the moon, and they took another remarkable Earthrise picture, a picture from Artemis 2 of the Earth over the surface of the moon. So I think that's kind of cool. By the way, the race to the moon was the thing that got me interested in science. It's the thing that got many scientists of my age originally interested in science and technology by watching us go to the moon in the 1960s and 70s. So that's, the closest object to us. The farthest object that humans have ever sent into outer space is Voyager 1. It was launched on September 5th, 1977. It flew past all the outer planets except Pluto. It's one of the greatest feats of human intellect that we've ever had. It's still transmitting information back to us since 1977. It's currently almost 16 billion miles from Earth. It's the first man-made object to ever leave our solar system. On February 14th, 1990, it was about 3.7 billion miles away from the Earth, and it was instructed to turn around from where it had came to look back at the Earth and take a picture of what it saw. And here's the picture that it saw. This is a picture taken facing towards the Earth from 3.7 billion miles away. If you look very closely right there, that little dot is the Earth as it looks from 3.7 billion miles away. Carl Sagan said about that what he called the pale blue dot, on it, everyone you ever heard of, every human being who ever lived out their lives, they're on a mote of dust suspended in a sunbeam. And again, you begin to see how small we are compared to the rest of the universe. I mean, this is a satellite or a spaceship or whatever that had not even left our solar system at the time. And this is yet how small we look. Of course, the nearest star to us is the sun. The sun is about 93 million light years or 93 million miles away. So in the fastest rocket ship we've ever made, it would take about 3 minutes to get to the sun. It takes a little over 8 minutes for light to reach us, traveling at 186,000 miles per second. And the sun, is this little red dot in the sky, but it's actually huge. If we were to get closer to the sun, this is about the size of the Earth compared to the sun. You can put about 1 million Earths inside of the sun. Of course, this is the closest star to us, but we recognize it as our sun. The next closest star to us is called Proxima Centauri. In the fastest rocket ship we've ever made, if we wanted to travel to Proxima Centauri, it would take about 50,000 years. 50,000 years to get to the closest star to us. And so when we start talking about distances to stars and other things like miles don't work anymore. So of course we use the scale light years. Some people think a light year is a time scale because it's got the word year in it, but of course it's not. It's the distance that light would travel in 1 year. It's still hard to imagine how far that is. How fast does light travel? 186,000 miles per second. That means if we were to shoot a beam of light around the Earth, it would circumvent the Earth about 8 times in 1 second. So in 1 year, light travels 5.9 trillion miles. So 1 light year is 5.9 trillion miles. Now, again, it's hard to imagine how big that is. So let me give you an example. Suppose you were to start counting one every second. So you start counting 1, 2, 3, and you count one every second. Well, how long would it take you to count to a million? It would take about 11.5 days, 11 and a half days to count to a million. How long would it take you to count to a billion? It would take almost 32 years to count to a billion. So I am more than 2 billion seconds old. I'll give you my age, at least more than 2 billion seconds old. But how long would it take you to count to a trillion if you counted one every second? It would take you 31,688 years to count to a trillion. That's 1 trillion, 31,680 seconds. Yeah, 31,688 years is a trillion seconds. And a light year is 5.9 trillion miles away. So Proxima Centauri is 4.25 light years away. That is a distance of about 25 trillion miles away. Traveling at the speed of light, it would take 4.25 light years to get to the nearest star. And that is, of course, only the nearest star. And why are we doing this journey? Because God says, as the heavens are higher than the earth, so are my ways higher than your ways. One of the most recognizable constellations in the universe is the Pleiades. It's actually mentioned in the book of Job, where God says to Job, can you bind the chains of the Pleiades? Can you loosen Orion's belt? Orion, another one of the very well-known constellations in the sky. Can you bring forth the constellations in their season or lead out the bear with its cubs? The bear is the Big Dipper. So God is talking to Job about these constellations we're familiar with. Do you know the laws of the heavens? Can you set up God's dominion over the earth? By the way, these stars are the Pleiades are the seven sisters, are all different distances from us. But in general, they're about 444 light years away. So still relatively close within our galaxy. It would take 444 light years or years traveling at the speed of light to get to some of the stars of the Pleiades. God mentions to Job the constellation Orion, which is another one of the most recognizable constellations in the sky. That bright red star up in the top left is Betelgeuse. It's a red giant star. That is about 642 light years away. So traveling at the speed of light, it would take 642 years to get there. And it's a gigantic star. Here's a close-up picture of Betelgeuse, but you can't imagine how big it is. If we were to take our whole solar system and put it on Betelgeuse, it would look like this. So this one star has a diameter about the size of Jupiter's orbit. It would completely engulf all the inner planets. It would reach nearly to Saturn and completely engulf Jupiter's orbit. This star that is gigantic in and of itself and is 642 light years away. Another feature of Orion is called the Orion Nebula. A nebula looks to us like a gas cloud or something. It's right here in this picture. And it is kind of a cloud of gas. In fact, it's a stellar nursery. If we were to look closely at the Orion Nebula, this is what it would look like. It's a place where there's hydrogen gas that's coalescing, mostly hydrogen, that's coalescing to form stars. And this is 1,344 light years away. So again, traveling at the speed of light, this is still relatively close, to be honest, and it would take 1,300 years to get there. Another beautiful picture out in the sky is this Cat's Eye Nebula. This is a star that actually exploded about 1,000 years ago. The gases ejected from it, it's 3,262 light years away. So it's taken 3,000 years for the light to get to us, but 1,000 years before that, it actually exploded. And it threw this gas out, and we see this beautiful Cat's Eye Nebula. Again, relatively close to us as far as cosmic scales go, because it's only 3,262 light years away. There's a picture of our Milky Way galaxy, if you could get far enough away from it. Of course, the spiral arms that look like clouds of spiral gas or something are the 200 billion stars in our galaxy. Our galaxy is a pretty large galaxy. It's 105,000 light years across. So again, it's hard to begin to imagine these distances. Remember, 1 light year is 5.9 trillion miles, and a trillion seconds is 33,000 years. And this is 105,000 light years away, only one galaxy. It's about a pretty large galaxy. And then our sun is right kind of in the middle of the galaxy, right where it would have to be in order to have a planet like ours to exist. If you're too close to the center of the galaxy, there's too much radiation to support life like us. And if you're too far from the center, there's not enough heavy elements to make a planet like the Earth. So we're in this beautiful spot in our galaxy that's 105,000 light years across. The closest large galaxy to the Milky Way is the Andromeda Galaxy. Here's a picture of it. It's 2.5 million light years away. Again, an insurmountable distance, an incomprehensible distance. Traveling at the speed of light, 8 minutes to get to the sun, 2.5 million years to get to the closest large galaxy. And that is just the closest galaxy to us. So the universe is incomprehensibly large. The Hubble telescope was told to take a picture of a point in the sky where they thought there was nothing there. So if you can imagine stretching out your arm and looking through a pinhole, so holding like a pinhole out at arm's length. This is the size of the dot they were looking at in the sky, and they pointed the telescope to a place where they thought there was nothing there. And this is what they saw. In this pinpoint of a spot, they saw all of these dots, and almost all of these, except for the one that has the little stars coming out of it, are galaxies. So a point where you think there's nothing in the sky, there's nothing but galaxies. In total, there are 100 billion galaxies that we can see, with about 100 billion stars. The farthest galaxies in this picture, when the light left them, they were 13 billion light years away from us. The universe has continued to expand, so they're now about 45 or 46 billion light years away from us. So we are looking at galaxies that are like 46 billion light years away from us, traveling at the speed of light. Well, we never get there because they're receding away, but if we could immediately jump there, it would take 46 billion years to get to where they are now. And this is just what we can see of the universe. There's much more of the universe that we can't see. In fact, the universe by volume is at least 15 million times larger, 15 million times larger by volume than what we can see. This is a computer simulation of what we think what we call the large scale structure of just a part of the universe is. It looks kind of like a spider web of filaments, but those filaments are galaxies. So what we're seeing are patterns of galaxies. The galaxies in our universe align on these filament lines. The universe is not uniformly distributed with galaxies. And again, from this viewpoint, you can't see a single galaxy. You just see these filaments of hundreds of billions of galaxies. The size of the universe is incomprehensible. In Isaiah, we learn something else about the universe and God's relationship to it. God says, "To whom will you compare me? Or who is my equal?" says the Holy One. "Lift up your eyes and look to the heavens. Who created all these? He who brings out the starry host one by one and calls forth each of them by name. Because of his great power and mighty strength, not one of them is missing." I mean, I just showed you some of the many galaxies in our universe and the picture that shows galaxies in a spot we didn't think there was anything. But yet, according to Scripture, God knows each star by name. He brings out the starry host one by one and calls forth each of them by name. So, to whom will you compare me, or who is my equal? And we can't even begin to see the stars and all the galaxies. And yet, Scripture says that God knows them all He calls them each one by name, and not one of them is missing. So we live in this, universe that we can't even begin to comprehend how big it is. It is immensely large. And that tells us something about God, how big he is, and also how different his ways are than ours. As the heavens are higher than the earth, so are God's ways higher than ours ways, and his thoughts than our thoughts. So when I don't understand what God's doing in my life, he says that's because my ways are different than yours, as the heavens are higher than the earth. So that's kind of the big. The next thing I want to talk about is the small. And again, I'm going to start by looking at a scripture verse, because this verse, Romans 1, is maybe, other than Psalm 19, the most famous verse on how we see God in nature. And it says, "For since the creation of the world, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood for what has been made, so that people are without excuse." So I want to take that and I want to actually now look at the small and see what can we learn about God from looking at the very small things, apart from what we've just done, looking at the big things. And according to this verse, we should see his actual qualities, things like his eternal power and divine nature. So what do I mean by small? Well, let's start with something familiar, a glass of water. We all know that water is made of H2O molecules, water molecules. And we, talk about molecules as if we understand their size, but it's quite hard to understand their size because they're so small. There are about this many water molecules in a glass of water. I don't even know what that number is. You can count the zeros. So in one glass of water, which I have right in front of me because I'm drinking, there we go. I just lost some water molecules. There are, huge number of water molecules, and molecules are actually very big in the subatomic world. As you know, molecules are made of atoms, and we often draw a picture of an atom like this. It's hard to explain how small an atom is. Again, this says 10 to the minus 10th meters, but what does that mean? Well, let me give you an analogy. Uh, I'm an avid golfer. In fact, I played golf today, and there are as many atoms in a golf ball as you could fit golf balls inside the earth. So in one golf ball, there are as many atoms as there would be golf balls inside the earth. Again, it gives you some idea of how small an atom is. And in my world, which I'll talk about in a little bit, an atom is gigantic. An atom is like a universe. But we live in an amazing time. We've learned to actually look at individual atoms. These are individual nickel atoms, and we can actually see them on the surface of a metal, of a substrate. We can now manipulate atoms and force them into exact places that we want. These are individual atoms that some company, I'll let you guess what company, actually, was able to manipulate atoms and spell something out. So here's where we are so far in our small journey. Water has a lot of molecules in it. The molecules have atoms in them, and atoms have at their core a nucleus. Now, we often draw an atom like this, but that's actually a terrible representation of an atom because it makes the nucleus look much, much bigger than it actually is. So let me give you some idea of how small a nucleus is compared to an atom. I mean, already an atom is extremely small compared to everything else. We saw that with the golf balls. But here's a picture of a city. You can probably tell what city this is, right? So right at the middle of this city is a Capitol building. And if I was to say that the nucleus is the size of a baseball, so in this analogy, the nucleus is the size of a baseball, and I'm going to drop it right in the center of the city. How big would an atom be? Well, an atom would be about 4 miles in diameter. If the nucleus was the size of a baseball, the atom would be about 4 miles in diameter. So when we draw pictures of atoms, like this, they're completely inaccurate because if you could see the orbits of the electron, you would not be able to see the nucleus at all, just like you can't see the nucleus here when I show you the picture of the city. All right, so we're getting smaller. We're going to get as small as we can. We know that the nucleus is made of neutrons and protons, and neutrons and protons are made of things called quarks. I've spent much of my career over 30 years of my career studying how quarks go together or put together in neutrons and protons. How big is a quark? Well, it's really hard to know. First of all, we know that it's less than 10 to the minus 19 meters. How small is that? Well, let me give you an analogy. So the difference in size between a single quark and a person is about the same as the difference in size between a person and the distance to the largest galaxy, or the farthest galaxy you can see with your naked eye, which is Andromeda. So the difference in size, let me repeat that, between a quark and a person is the same as the difference in size between a person and the distance to the farthest galaxy you can see with your naked eye. So quarks are unimaginably small. Well, how in the world do we study them? Here's where I'll talk about my research a little bit. Well, we build a big collider. Why do we build a collider? Because we want to know what the proton is made of. It's made of quarks. There's no way to take a proton apart, so we have to do something to be able to probe inside of it. And the analogy I give is it's like if you wanted to know what a car was made of, but you didn't have any tools to take the car apart, what would you do? Well, if you're a particle physicist, you'd get two cars going really, really fast and you'd smash them against each other and they break into smaller pieces. And that would tell you what the car is made of. So we do the same thing with protons. We get them going nearly the speed of light and we want to smash them together. And so we build this tunnel. It's about 17 miles in circumference. It's on the border of Switzerland and France. You can see this dotted line with Switzerland being above and France being below. The lake you see is the Lake Geneva. The city you see just in the background of the lake is Geneva. And this is the tunnel, the Large Hadron Collider, where we smash protons together. The tunnel is about 100 meters underground. If you were to go underneath in the tunnel, you would see these blue superconducting magnets. They bend the protons around the tunnel. If you were to open them up, they'd look like this, these magnets. You can see the size of a person. Over on this end, you see these two pipes that have these covers on them. Those would carry protons. One group of protons going in one direction, one pipe, and one group of protons going in the other direction, the other pipe. We actually put protons in little tiny packets that are a few centimeters long and maybe a millimeter thick or even thinner than that. And so think of like a little packet of protons, a couple centimeters long and maybe a millimeter wide. And we put those packets of protons about every 15 feet apart. So around this whole ring, when it's running, it isn't running when there's someone in the tunnel, you've got these packets of protons moving in opposite directions. Here's an artist's depiction of that tunnel. And what we want to do is bring the protons in from one direction in the tunnel and bring the protons in from the other direction in the tunnel, smash the protons together, and build a big detector to see what comes out from the collision. The protons smash together, get this, 40 million times a second, 24 hours a day, about 6 months of the year. So 40 million times a second, the protons smash together, and we try to take a picture of that with the camera. The camera I work with is called Atlas. It's a gigantic detector. Here's a drawing of it. You can see people here at the bottom and people at the top. That gives you some idea of the size of the detector. It's about the size of a 8 to 10 story building. It's about half the length of a football field. And every 40 million times a second, protons come in from each direction. They smash in the middle, and the computer takes pictures that look something like this. This is the debris from the collision of protons. And from this debris, we understand things like quarks. And so we really do know that quarks exist. The kinds of images that you see here would not be possible if our understanding of the subatomic world were incorrect. And so we know that there are these things called quarks, which are, again, so small that you can't imagine the distance, the size of a quark from a quark to a person is the same distance as from a person to the farthest galaxy you can see with your naked eye. The question that we're trying to ask is, what is a quark made of? If any of you know, please let me know, because as far as I know, no human has any idea. Well, we have ideas, we haven't discovered it, but if you know, let me know, we'll win a Nobel Prize. But that's one of the things we're looking for. Is there something smaller than a quark? Why do I go through all this? Because we've moved from the macroscopic world, the world that we're familiar with, to the microscopic world, the world of atoms and things smaller than the atoms. And what we want to do is say, what do we see from this microscopic world that tells us about God? Now, it turns out that these two worlds are not equal. The kinds of things that we are experience in our everyday macroscopic world are totally different if we were to shrink to the size of an atom or smaller. And so, what would you see if we were to shrink to the size of an atom or smaller? Well, the science that describes this is called quantum mechanics, and it's a very strange world. So, I want to give you some idea of what we would see if we were to shrink to the size of an atom and encounter this quantum mechanical world. And everything I'm going to tell you are things that have been experimentally shown to be true. So as bizarre as the quantum mechanical world is, the very small world, these things have all been shown to be true. So the quantum mechanical world is very strange. Let me give you some examples. Within the quantum mechanic world, it's possible to be in two places at one time. So you could be at home doing your wash, and at the same time, you could be laying on the beach in the Bahamas. So that's quite nice. And this is true. You can actually be two places at one time. That is, until someone actually sees you. So when someone actually sees you in one place, you cease to exist in the other place, and you end up only in the one place where you are seen. So, you have to hide yourself from your kids if you want to stay doing the laundry and being at the Bahamas. In the quantum mechanical world, suppose that you had the capability of throwing a basketball about 20 feet in the air, and in front of you was a wall that was 25 feet. Well, would that basketball ever end up on the other side of the wall? Well, of course not. That can't happen unless you're in the quantum mechanical world. And in the quantum mechanical world, every once in a while, when you throw the basketball, it would end up on the other side. We actually call this tunneling because it's as if the basketball tunneled through the wall. And this really happens. Another thing that happens is things called virtual particles can appear. So suppose you're sitting down at Thanksgiving and you're ready to eat your turkey. Well, what can happen is these particles can appear from nothing. You could have like two pieces of cherry pie appear and then disappear. And they're not really cherry pie because one is a particle and one is an antiparticle. So one is cherry pie and one is anti-cherry pie, whatever that is. And in fact, this happens all the time. We call them virtual particles. They appear from the space-time fabric of the universe or from nothing, from nowhere, and then they disappear again. And this really happens. We'll talk more about that. Suppose you wanted to play baseball. Well, we know how baseball is played in the regular world. You throw a ball, it curves or goes straight, and the batter then hits the ball. But suppose you wanted to try to play quantum baseball. What would that look like? Well, it's hard to depict, but it would look something like this. Due to something called Heisenberg's uncertainty principle, you can't know the location and the momentum of any object at any time. So it looks something like this, and it would actually be even more bizarre because it might look something like this. All right, so what was that? Let's look at that again and see what we see. So what happens is the baseball momentarily turns into two bowling balls, or a bowling ball and an anti-bowling ball, because things can turn into virtual particles. So for a moment, the baseball would disappear. It would turn into two particles, or a particle and an antiparticle, which actually together have much more mass than the baseball. But you can't get something from nothing. So of course, those particles would disappear and go back to the baseball. And this is how you would play quantum baseball. I think the pitcher would have the advantage. It'd be very hard to hit something that you don't really know where it is. And it'd be really hard to hit it when it actually turns into the bowling balls. So what does this look like in a proton? Well, a proton we know is made of three quarks. It's actually made of two up quarks and a down quark. But that's not all it is. It's much more complicated. Because there are these things called virtual particles, every once in a while, a top quark and an anti-top quark will appear inside the proton. And this is hard to imagine because together, the top and the anti-top quark actually weigh 350 times more than the proton itself. So, that's like me walking along and all of a sudden, I don't know, two elephants pop inside my body that together weigh 350 times more than I do and then go away. And this happens inside every proton. Well, they go away because you can't get something from nothing. This happens inside every proton and every neutron in the whole universe. Inside your body, every proton and neutron is having virtual particles pop into existence and then go out of existence. Now, this is amazing because these virtual particles slightly change the mass of a proton. And the mass of the proton is finely tuned to allow life to exist. If you were to change the mass of the proton by just a fraction, a series of events would happen that basically means there'd be no life in the universe. The proton might decay depending on which way you change the mass, or other things would happen. So get this, if it wasn't for virtual particles that pop into existence and go out of existence in unimaginably small times inside every proton and neutron in the universe, if it wasn't for these virtual particles, there'd be this cascade of events in which life would not exist. It's really remarkable. So, these are some of the aspects of quantum mechanics. It's very weird. It's very strange. You may go, well, why are you telling me all these things about quantum mechanics? It's making my head hurt. What's the point? Well, here's the point, and I've kind of started to say it. Life is only possible because of quantum mechanics. If there is no quantum mechanics, then all of the molecules in the universe are simple single atoms or diatomic molecules, that is, two atoms. This is what the universe would look like, every molecule in the universe, if there wasn't quantum mechanics. But because there's quantum mechanics, we have molecules that look like this. We have DNA, we have proteins, we have life. So when we look at the variety of life just on this planet, you can say it's all there because of quantum mechanics. It's all there because of this strange world of quantum mechanics. Now, I don't know about you, but if I was to make a subatomic world, a small world, I would probably just make a miniature version of the big world. I would make, just little small Lego blocks or something that you put the whole universe together. But God didn't do it that way. God did something totally different. When he made the microscopic world, he made a world that was entirely different than the macroscopic world we live in. And so you begin to ask questions, is it comforting or disturbing that God is so big and we're so small? Is it comforting or disturbing that God made a subatomic world where objects can be at two places at one time, or objects can pop into existence from nothing? Is it comforting or disturbing that God's thoughts and his ways are higher than your ways? As I said, this is a question that's been around forever. The oldest book in the Bible is the book of Job, and you know the story of Job. He was a righteous man, and through a series of circumstances, he lost everything. He lost his children, he lost his wealth, he lost his health, and the book of Job is full of questions for God. Why do things like this happen to good people? And all of Job's supposed friends kept saying to Job, well, you must have done something wrong. Because, if you had been truly a righteous man, none of this stuff would have happened. God wouldn't allow this kind of injustice and tragedy to occur for someone who is truly righteous. And for 37 chapters in the book of Job, Job and his friends debate about what God is doing and where is God and why would God do all this? And then after 37 chapters of that, God speaks. And Job 37:1 says, the Lord answered Job out of the whirlwind and said, who is this that darkens counsel by words without knowledge? Gird up your loins like a man, and I will ask you, and you will instruct me. And for the next 4 chapters, God just asked Job a bunch of questions. He asked him things like, where were you when I laid the earth's foundations? Tell me if you understand. Who marked off its dimensions? Surely you know. You see the sarcasm there. Who stretched a measuring line across it? On what were its footings set? Or who laid its cornerstone? And he asked those questions about Orion and Pleiades and the Big Dipper that we saw earlier. He asked Job, can you feed the wild animals? Can you bring rain or wind? Can you cause the morning to appear? And after God questions Job for four chapters, Job gets the point. And it's the point that we should get as well. And after all this time, here's the words of Job. He says, my ears had heard of you, but now my eyes have seen you. See, before Job's trials, he had only heard about God. He had this, relationship with God, but it was distant in some sense. The trials drove him to God. And he says, now my eyes have seen you. Now he knows God in a much more intimate way. Because God brought trials into Job's life, Job knows God better. And that is God's desire for us. When we go back to this verse here, where we started, where God says, my thoughts are not your thoughts, neither your ways, my ways, declares the Lord. As the heavens are higher than the earth, so are my ways higher than your thoughts, or your ways and my thoughts higher than your ways. Because our ways are different than God's ways. My ways are about having more stuff and being more comfortable or advancing in my career. But God's ways are about getting to know him better and trusting him more. My ways are about changing the circumstances. God's ways are about him walking with me through the circumstances. The circumstances are nothing to him. He made the universe. He made this gigantic universe. He made the big universe that's so large we can't even comprehend it, and the small universe that's so bizarre we can't comprehend it. The circumstances are nothing to him. He's big. So when we have those circumstances in our life that we can't figure out, what are we supposed to do? We're supposed to trust God. We're supposed to recognize that the heavens are higher than the earth and his ways are higher than our ways. I say a joke that when I'm really struggling with God and I don't understand what he's doing, and I say to him, what is going on? His answer to me is, don't you recognize the message of quantum mechanics? And the message of quantum mechanics is the same as the message of Isaiah 55, that God does things different than me, but his ways are for my benefit. In the same way, I wouldn't be here if it wasn't for quantum mechanics, but it's so bizarre. This is God's ways. They are different than ours, but they're always designed for our benefit. And we know that because, as Isaiah says here, as the heavens are higher than the earth, so are my ways higher than your ways. I find this interesting. God could have said any distance. He could have said, as Jerusalem is as far as Jerusalem is from Rome, that's how different my ways are than your ways, and my thoughts than your thoughts. As far as Spain is from Jerusalem, but he didn't. He chose the farthest distance we can ever imagine, the heavens. And he said, that's how different I am than you, as the heavens are higher than the earth. And to me, that's both challenging and it could be frightening, but it's interesting because there's one other thing in Scripture that God describes as high as the heavens are above the earth. Not just his thoughts and not just his ways, but also remarkably his love. He says, for as high as the heavens are above the earth, so great is his steadfast love towards those who fear him. We have this God who's not only so different than ours, more than we can imagine, but his love towards us is described in the same way, higher than we can ever imagine. And as you know, the message of Christianity is all based on this, that God demonstrates his love for us, and this while we were still sinners, Christ died for us. He showed his love for us by sending his son to rescue us from our sin. I mean, this is really remarkable that the God who spoke and made this universe that is so large and so bizarrely small is the one who came and died for us. And the message of Christianity, of course, is that we can have a relationship with him. The creator of the universe wants to walk with us through those trials of our life. because his way is about us getting to know him better. This is a relationship that is dynamic with its ups and downs. And when I have those downs, I look to the size of the universe and God's ways and recognize that it's done out of his great love for me. All right, so that's kind of what I have, and we can open it up for questions.
First of all, thank you, Mike. That was a wonderful journey. The biggest and the smallest, both ends of the journey were amazing, and quite a testimony to God's power and grace and love towards us. So thank you for that. One question I'll start off with. You had mentioned that the size of the actual universe is much larger than our visible universe. How could you say again how big that was, much bigger, and how we know that it is that large?
Yeah, so by volume, it's minimally 15 million times larger than the visible universe by volume. And the way we know that is we can see the curvature of the universe. So let me give you an analogy. Suppose you were to watch a ship, go over the horizon and get some measure of the curvature of the Earth. Well, if the ship went really far, you would think the Earth is almost flat, but you could tell that it has some curvature. If the Earth was really big, no matter how far the ship would go, it would still look flat. And so that would give you some minimum size of the Earth's curvature. So the universe has a quote curvature. It's not two-dimensional, it's three-dimensional, so it's harder to describe. But we can look at the universe and measure the minimum size of that curvature. And it basically looks flat. It's as if it goes on almost forever. And because it looks almost flat, we can say, well, how good are our measuring instruments? How well are we measuring this curvature? And then you get a minimum size of what the curvature is, and therefore a minimum size of what the universe is. If that made sense.
It makes some sense, yes. It's kind of mind-blowing, but yes.
Yeah, it's hard to imagine, but if you looked out and the Earth looked flat, then you would say, well, how good is my measuring instrument? If it does have some curvature that I can't quite measure, what's the minimum size the Earth would be? And we do the same thing with the universe.
Yeah, great. So we'll open it up for questions, either those in the room or on Zoom. Please jump in.
I have questions. I could talk to this guy for hours. I also do research. I have 11 patents. I work in applied physics. And number one, Job did do something wrong. He presumed upon God and said, all of this wonderful stuff that I've got is because I'm God's buddy. And he got called on that at the end because God basically said, you ain't my buddy, you're my creation. So the question I have, I've been doing some research in evolution, and the question I have is, where does all the iron that's circulating beneath our feet come from? The universe consists of primarily gases. And yet without this big ball of iron, we would not exist because it protects us from the sun.
Yeah, so iron is created at the very end of some star's lifetime. All of the elements of the periodic table up to iron are created basically in red supergiants and red giants near the end of their life. So they end up using all their hydrogen fuel and they start to burn helium. And as they burn helium, they're fusing. So every time you fuse, you make heavier elements.
Right.
And eventually you make all the way up to iron within red giants and supergiants, super red giants. The elements above that with atomic weight actually are created in supernova because you need even more energy to get the elements above iron.
Okay. So then how did it all end up beneath our feet?
Yeah, so our sun is at least a third generation star. So the first generation of stars were made of hydrogen and helium, and when they died, they made many of the elements of the periodic table. Those elements then were spread throughout the universe, and everything other than hydrogen and helium is a very small fraction of the elements in the universe. But those coalesce into a second generation of stars, and those stars now have not just hydrogen and helium in them, but iron and other elements, and we can actually see their spectrum and see what they have. And then those stars, some of those stars exploded, and the remnants of those stars are what formed our sun. So
Okay.
our sun started with the iron and the heavy elements that came from two generations of previous stars that created them.
So then we throw that onto a timeline, and the iron has to be here before, and we have to be in the Goldilocks zone before you even have an idea of life existing.
Right. So we know the physics and chemistry that creates the iron, and to get a planet like the Earth, the quickest time it takes, since you have to get through two generations of stars, is about 9 billion years, and that's when our sun was created. So it really is the quickest time it would take to make a solar system like ours is what happened, as if the universe, had us in mind from the beginning.
Okay. Yeah. Well, I've just, to just go through a timeline of probability of things happening. I mean, you have to have the Earth exactly where it is, made of exactly what it's made of, before you can even contemplate having life here.
Yeah.
And so the probabilities of all of this just go
Yeah.
berserko.
Yeah, without God's guiding hand, the probabilities are really low.
Exactly.
Yeah.
Yeah, that's kind of the point. Thank you.
Yep.
Well, I have a question. Kirby Hansen from uh, uh, Los Altos, California. And my question is about quarks. But my understanding is that there are a number of mathematicians who now think that, well, actually, this has been going on for a while, I guess, but who think that quarks are actually made of strings. And so they've got this mathematical theory called string theory. And I don't have any clue as to how this could possibly be, but could you talk a little bit about that, or does it make any sense? Or
Yeah, I mean, so there are some reasons to believe that string theory might be true. We have a theory of quantum mechanics that works at very small difference distances. We have a theory of how gravity works called general relativity. And those two theories, although they're both shown to be true, are incompatible with each other. So there's got to be some way that you can reconcile those two theories, and string theory would allow that reconciliation. That's one reason why people like it. String theory has a lot of implications that seem bizarre, but they could be true. The idea within string theory is, again, I know the words, I don't know exactly what they mean, that the universe at its most fundamental level are vibrating strings of energy. And these vibrating strings can vibrate in different ways, just like the strings of a guitar can vibrate in different ways. And depending on how they are vibrating or how they are put together, they make the different fundamental particles. So you vibrate the string in a certain way, you make an up quark. You vibrate the string in a different way, you make an electron, the fundamental particles. And there's debate whether we could ever really show string theory to be true. There are implications of string theory we might be able to show are true. But again, as you said, mathematicians, theoretical physicists put a lot of credence in it because it has the potential of solving lots of problems. My understanding, I don't know the math of string theory. My understanding is it's very challenging. I've heard there are only a few people who actually can do the math of string theory. But who knows? So uh, string theory says the universe is made of vibrating strings of energy as the most fundamental building block of the particles and forces in the universe.
Yeah, hi. Kind of along that line, I just had the thought, is there a limit to, do we know an actual Planck length that limits the size of a quark or a string?
Yeah, there is a Planck length, which some people think we don't know if space is quantized. That is, if you divide the distance to your wall by half, would you ever get to
Yeah.
a point where you can't divide it by half anymore because it's quantized? And that size would most likely be the Planck scale, which to be honest, I don't remember what it is. 10 to the minus 43 meters or something is what comes into my brain, but I don't remember. I could Google it, but it is possible that the Planck length is the smallest length in the universe that can't be further subdivided.
It can't
But
be zero.
quarks are much, much bigger than that. Quarks are as far, well, we don't know the size of quarks, but the maximum size they are is 10 to the minus 19th meters, which is orders of magnitude, greater than a Planck scale, which is 10 to the minus 40 something or something like that. I can look up what the Planck scale is, or somebody else could, but because I don't remember off the top of my head.
I think
But
it was something like the height of a human being to the size of the universe or something like that. It was just,
yeah, yeah. Let me look it up really quick. It's 10 to the minus 35 meters. Right.
Hmm.
So, a quark, which is a maximum size of 10 to the minus 19th meters, is still, you know,
Yeah,
20 orders of magnitude, 15 orders of magnitude larger.
but it couldn't be 10 to the minus 36. They know that.
Um, what could it be 10 to the minus 36?
The Planck length, you said that it was 10 to the minus
No,
35.
The Planck length is known.
Oh,
But whether or not that's the smallest possible length is unknown.
okay, yeah.
But if there is a smallest possible length, the Planck length is a good candidate for that.
Yeah. The other thing I actually came up here for is I was thinking, looking at the scale from quantum to cosmic, um, a lot of objection to Christianity is that we're such an insignificant little speck in the universe, and we're little specks on that speck that we can't possibly have any importance. The universe doesn't care about us. But what I'm hearing tonight is that size is irrelevant to importance. So,
Yes.
like a larger person isn't more important than a small person.
Yeah. In fact, I think that's really crucial to understand. Size is not relevant to importance. We certainly share a very unique place in the universe that's life friendly. The example I always give, people will say, if God cares about humans, then why do we have this one tiny planet that seems habitable and the rest seems superfluous or uninhabitable? And the short answer is you need all the other stuff if you want to create a planet like the Earth. If you want to create a planet like the Earth, you have to start with the Big Bang and you have to have the right expansion rate and the right amount of matter. So you end up getting a universe this big. So the space is not wasted. The space is actually relevant to creating a universe that has a planet like the Earth. The analogy I give is back to the Saturn V rocket. There's this little tiny part at the top that is habitable. So if you make the same argument, you say, well, the rest then is unnecessary. But of course, the rest is entirely necessary if you want to have that habitable part complete its mission.
Yeah, thank you.
I had a I had a question about sorry, I'm seeing my wife's name on the Zoom here. But my name is Mike, by the way, and thank you so much for a great talk. My son Elijah is here with me. Um, that's him. So got a question about the experimental evidence for quantum mechanics. And you mentioned a few different quantum principles. I'm familiar with the experimental basis of our knowledge of quantum tunneling. But could you maybe explain a little bit about how we know things like the uh, the observer effect? When you see a particle, it ceases being in two places at once. Do we actually how do we know that something existed in two places until we saw it? And also the uh, matter antimatter effect, the spontaneous uh, popping into existence of these things.
Yeah. So the two places and once comes from the mathematics. We know that the wave function is a probability distribution, and the wave function is a probability distribution of where the particle is. And so until you actually make a measurement, the wave function, which tells you the probability where the particle is, can be at multiple places at one time. So because when you make the experiment, you get the probabilities correct. You're assuming that that probability distribution is correct before you make the measurement. That is, that it really is in all these places at one time. And there are experiments you can do, like shooting, like the double slit experiment, where you shoot a single electron through two slits and it makes a diffraction pattern, which can only happen if it goes through both slits at one time. And so the fact that a single electron will give you a diffraction pattern basically says that the electron went through both slits that were separate places at the same time. As far as the virtual particles are concerned, they occur so quickly that you can't measure them, but you can do calculations. You can do experiments and say, what would I get if there were no virtual particles, and what would I get if there were virtual particles? And the answer is always if there are virtual particles. There are other things that we know happen that our theory says only occur if virtual particles exist. Radioactive decay is one of those things. Radioactive decay occurs through a virtual, what we call a vector boson. It's a virtual particle. It's not quite the same as the particles that pop into and out of existence, but it's along the same line of reasoning. It's still what we call a virtual particle. So every time there's a radioactive decay, it's because these virtual particles basically existed. So that's kind of a short answer to both your questions.
Thank you. That was really helpful. I appreciate that a lot.
Good.
One other question. One of the seemingly the major apologetics for the faith is the idea of the fine tuning of the universe. And I recall years ago when I was at an RTB conference, they were talking about the mass of the universe and making the analogy that if it were different than the size of one dime, that would be, there'd be no life. And then I think that was revised when it found other features were fine-tuned in addition to that. And more recent thing was the dark energy constant of 10 to the 120th power, if it was any more or less. Now I hear that's been a bit refined also, and other factors have been brought into play. So what is your thought on how the fine-tuning argument can be used in Christian apologetics, and how do you use it?
Yeah, so it's an interesting question because what is today? Tuesday? On Saturday, I was in Pittsburgh at a conference for the Christian Scientific Society, and I gave a talk on the fine-tuning of the universe. So I just gave a talk on this. I think that those things are still correct. The cosmological constant is different from our calculations by an order of 10 to the 60th to 10 to the 120th. So there's that means we're missing something, because when we calculate what we'd expect it to be, it's off by a huge amount. But yet, if it was any bigger, then we would not have stars and galaxies form. So it seems to be finely tuned. There's so many things that are finely tuned. The energy density of the universe is finely tuned. Whether, and we're talking about the amount of matter you would put into the universe when it's, well less than a fraction of a second old. And at that point, if you were to add a dime of matter to the universe, it would affect it. Now, we have understandings of how the mass energy density of the universe works itself out through inflation and things like that. These are mechanisms that help solve the problem, but even the mechanisms have to be finely tuned. So I think the fine-tune argument is a good argument that there seems to be a designer behind it all. I mean, most scientists, not all, but most recognize, well, almost all scientists recognize that the parameters of the universe, things like, the speed of light and the mass of the proton and these kinds of things are in are very small range that allow life to exist in our universe. That if you did change them just by a little bit, you'd either have no universe or universe inhospitable life. Almost everybody recognizes that. Um, the things you get are, well, maybe they're fixed, maybe those constants are fixed by the laws of physics or something. So even though we can say that if you can change them a little bit, then life doesn't exist. Can we even change them? Is it possible to change them? But to me, that doesn't solve the problem, because if the laws of the universe force the constants to be in the small range that is necessary for life, you just push the problem back to the laws of the universe rather than the constants themselves. Um, and then the other option that most scientists believe is a multiverse. If we live in a multiverse, then, every other universe has different laws of physics. Very few of them can support life, and ours can, and we're just in the right one. Uh, so I still think the fine-tuning argument is one of the best arguments for a designer behind the universe. So I still use it a lot, and those examples you gave, I think, are still relevant. Maybe not exactly the numbers that were given at one time, but yeah, they're still relevant.
Okay, thank you. Anyone else on Zoom have a question?
I had one last, maybe quick question. My son and I were talking earlier about how some of these quantum mechanical principles, um, I don't know what the word is I'm looking for here, imitate the things that Jesus does after he's resurrected, passing through a solid barrier. Uh, yeah, that kind of thing. Is there, I guess what I'm trying to ask is just, is there any potential carryover from the quantum world to the macroscopic world? Or is
Yeah,
it?
there actually is. I mean, in reality, I talk about it as if they're two separate worlds, but they're not, right? We're made of the quantum world. So, in theory, you can see quantum effects in the macroscopic world. They're just so small that they're imperceptible. Um, but yeah, they actually do. Now, how I personally don't think God does miracles by manipulating the quantum world, but somehow he manipulates nature to do miracles. And, there's lots of theologians with lots of different ideas. So I'm not going to speculate because I don't know. But yeah, in theory, everything in the quantum world carries over to the macroscopic world. It's just, I'm going to pick a number from the hat. It would be, if you were to make a measurement, it might be in the 20th decimal place, and your measuring device can't measure that carefully. But in theory, we live in a quantum world. And by the way, there are things now where they can make certain macroscopic collection of objects show quantum properties. So you can make a macroscopic collection of particles of molecules, for instance, actually show quantum properties in the macroscopic world. This something called a Bose-Einstein condensate does that actually.
Thanks. That's fascinating.
Yeah, it is.
And the particle being in two places at once, seems a few years ago there was it was an experiment was published where they took a single atom that was being suspended in a chamber, hit it with two differently tuned lasers, and the atom separated into two different positions just because of energy states.
Yeah, I'm not familiar with that. Certainly, there's something in quantum mechanics that I didn't talk about called entanglement,
Yeah.
in which you can take two atoms that have a certain relationship, an entangled relationship, and separate them, and they still have, in theory, you could separate them huge distances, and they still are connected to each other.
What
And
happens to one happens to the other.
yeah, this
Yeah.
is because in quantum mechanics, particles are described by waves. And in the same way, you can have a wave that covers a huge area. you can have these two particles with two waves that cover this huge area, and so they can communicate.
Is that wave,
Particles,
is
yeah.
that wave just a statistical wave?
No, okay, now you're getting into the philosophy or the interpretations of quantum mechanics, which are much less well understood. But the wave describes the way nature works. Whether or not the wave is a real entity or whatever is, you can find whole articles written on that. But we do know that the wave describes how nature works. So in the same way that a wave can spread over a distance and therefore in some sense be in two places at one time and communicate over these large distances, that's what quantum mechanics does.
Yeah, the other thing I was thinking is information theory has become a really large subject in the sciences. How does that apply at some point to what you're doing? Where the information comes from? I mean,
Yeah, I don't think we no, we usually don't formally talk about information theory in particle physics.
although you're dealing with information.
We deal with complex information. Yeah, we were doing, you know, artificial intelligence before it was artificial intelligence in some sense. Yeah.
Okay.
From my reading of the Bible, I believe there's a separate universe that's spiritual in nature. It's where God exists, but it operates under its own physics. So they can do things that to us is just impossible. In your research, have you ever hinted at or possibly seen any evidence of a spiritual universe?
Yeah, not in my research, but I mean, different people have different understandings of what you just said. My take on it from scripture is pretty similar to what you just said. I believe the same thing. Where is Satan when he talks to God in the book of Job? I think it's for lack of a better word, a different universe with different laws of physics. I don't even know exactly what that means or if it's a physical universe or exactly what. But yeah, so I kind of agree with you. But what I often say is you have to use the right tools to make the right measurements. You can't measure the distance to the moon with a thermometer. And the tools I use are all physical tools to measure physical quantities.
Yeah.
So I'm
Okay.
most likely not going to see spiritual realities by using physical tools to measure physical quantities.
Okay. Yeah. Yeah. I've always wondered, like, God's building a whole new heaven and earth somewhere. Where's that construction zone at?
I don't know. Yeah.
And then I go back to, you guys talk about Big Bang and all that sort of stuff. And yet I go back to the Bible and it says, in the beginning, God, period.
Yeah.
God is the source of all energy, all matter, all everything.
Yeah. Ultimately, that's true.
And so to me, the spiritual energy of God was then converted into the physical universe that we live in somehow.
Yeah. Well, I don't know. It doesn't say that specifically. So
But
God's,
there's no other source though.
well, it says he created. You can speculate how he did it and what that means, but yeah,
Yeah.
I believe
Okay.
he created.
Yeah.
Yeah.
I got a question. The the CERN collider that you were talking about, they use protons and they smash the protons. Is there any reason why they use protons? Is there some other particle that they would possibly use, neutrons or I don't know, something else? What's the
Great question. So, in order to accelerate and control the particles, they have to be charged and they have to be stable. So there's really there's maybe six possible particles: protons, antiprotons, electrons, anti-electrons. And people have talked about muons and anti-muons because they're semi-stable, but they have to be charged and stable. And so you have very limited numbers. Neutrons are stable, but they're not charged, so they don't work.
what about electrons?
Yeah, electrons will work. We have machines that actually collide electrons. Actually, the other thing we can collide are ions. So if you take a gold atom, for instance, and strip off a couple electrons, now you've got a gold atom that's positive, and you can actually collide that. So we actually do collide. I don't know if they're gold nuclei or gold ions, but the nuclei would be positive charge. So at CERN, we also collide gold. It's much heavier. It's much more complex because, it's like smashing two Mack trucks instead of two motorcycles or something. But yeah, we anything that's charged and stable. So you can take any nucleus because that's going to be charged and stable and smash that as well. Protons are just a nice. They're much easier. It's easy to get protons, and they're relatively heavy compared to electrons. And the heavier they are, the higher the energy. So that's one of the reasons we use protons. But historically, we've had machines that shoot electrons as well.
Oh, okay. I didn't know. At CERN, you actually do that.
They did it at CERN for a while in the
Uh-huh.
same tunnel that they now the proton machine. Stanford's machine shot electrons on positrons, which are positively charged electrons. So I did my dissertation at Stanford with a machine that fired electrons on positrons.
So when they smash electrons, do they does what particle comes out? Because
So when I talk about, the analogy of smashing cars, it's actually a bad analogy in some ways. So the better answer is Einstein's equation E equals mc squared. So what does that mean? It means energy equals mass, E equals m. The c squared is irrelevant actually. So I can change energy from one form to another. So if I drop my pen, I change potential energy to kinetic
right.
energy. So when we smash particles together, we can actually change the kinetic energy of the collision into mass. So we create mass all the time because mass is just a form of energy. So really, we don't well, we can break the proton into smaller parts, but mostly we take that energy of collision to actually create more massive particles that would normally not exist in nature, except near black holes and things like that, because normally there's not enough energy in a density, energy in a small region. But by smashing protons together, we make these super high energy densities. Therefore, we create particles that haven't existed since right after the Big Bang or only like near black holes.
Is that how you get particles that are really, or atoms that are maybe not? But I'm just thinking about the periodic table has these really high numbered atoms that they
Yeah,
say
that's
unstable.
done a different way because again, nuclei are much, much
Yeah.
bigger than what we're dealing with.
Right.
So
Okay.
we're creating fundamental particles that don't exist very often in nature. They
Okay.
do because nature has high energy collisions, but we're creating like the Higgs boson is a fundamental particle that weighs 125 times more than a proton. Where do we get the energy to create that? From the kinetic energy of the protons that collide.
Got it. Okay, thanks.
That's a great question.
They're talking about energy with subatomic particles. They seem to just always have energy. The energy is never lost. It might be reconfigured. Where does entropy come in, and why don't they seem subject to losing energy? I mean, Scripture says Christ was not only the creator, he was the sustainer of creation. Are we getting into a spiritual area as far as what sustains subatomic particles?
Well, again, you're asking a theological question in some sense. So I will ask my friends who are Christians and scientists, a hypothetical question. If God were to leave the universe, would it keep running, or does he have to actually be interacting with it to sustain it? And you get different answers. I'm of the belief that a good watchmaker can leave the watch alone and it'll keep running. So my personal belief is if God were to leave the universe, which he doesn't do, it would keep running because it works so well. But not every scientist or theologian that I know agrees with that conclusion.
You have to ask the purpose question.
Question, you brought up radioactivity. I don't know how much you know about that, but maybe you can answer this question. One thing I always wondered about was, each radioisotope has a particular decay rate. Is that something, and we can measure the decay rate, but is that something that if we didn't measure the decay rate, we could have predicted it ahead of time based on our equations and what we know about radioactivity and physics and such? Or is that something that we had to actually measure to find the answer to?
That is a good question. Again, I don't know the answer. I do know that there are certain relations. So, I mean, I know the radioactivity at the particle level, which is what we call intermediate vector bosons that allow for things like beta decay. And those, there were certain mass relationships that were predicted based on the fundamental theory for those fundamental particles. But that doesn't totally answer your question. So, yeah, I'm not sure the answer to your question.
Okay.
My guess is you could, for certain reactions, you could probably make some reasonable estimates based on the known physics, but I'm not sure.
Okay. Reason why I was coming from that was just the young Earth creationist viewpoint and such as it's like, I wonder if you could just show the equations, say, look, this is how it works.
Yeah, I mean, the young Earth creationist objections to radioactive dating can be easily
Oh,
refuted.
yeah, I'm sure. Yeah.
Yeah,
All right. Thanks.
yeah.
Well, question about the Higgs boson. So you mentioned it earlier, and apparently it was discovered a number of years ago. But with the work that's going on at CERN, are you recreating Higgs bosons?
Yes. So my research right now is studying properties of the Higgs boson. I can't remember the exact number over the last, it was discovered in 2012 and we create, I don't know, I'll pull a number of that hat, one every minute or something. I could look it up. I forget what it is. But yeah, we've now compiled many, many more Higgs bosons than what was originally in the discovery paper. And we are trying to study its properties as carefully as we can to see if it's exactly the Higgs boson that theory predicts or if there's something un not predicted about it that would give us more insight into the universe. So yeah, I've spent the last 12 years, 13, 14 years studying the Higgs boson, actually.
Thank you.
Hmm.
Hi.
Hi.
Really appreciated your talk. And on both ends of the spectrum, it was fantastic. Something you said to an earlier question was that, if the watchmaker walks away from his creation, it would still work perfectly. And as that relates to what you're talking about, overall, I was wondering, how do you account for sin when at the fall, nature was affected? Um, and yet, I mean, we see these wonderful things of how everything is so fine-tuned.
Yeah.
How do you account for that? Or
So
does it?
in my old Earth perspective, nature wasn't affected by the fall. The relationship between God and man was affected. So most old Earth creationists would argue that nature was not affected by the fall.
Okay.
Yeah, and you can go to Romans 5, I think, where God talks about nature groaning. But in that context, it doesn't say that the groaning came because of the fall of man. So there's theological questions there that we could talk about. But yeah, in an old earth perspective, the thing that changed with the fall is the relationship between humans and God, not nature itself.
Okay. Thank you.
Yeah.
I appreciate you showed the importance of quantum mechanics to life and to have life here. And I understand one of the things that I'd heard is that fusion in the sun would not have happened without a quantum process. Could you tell us both how that happens and give us some other examples of quantum processes that lead to things that lead to life?
Yeah, so I'm not sure about fusion. I don't know a lot about, I mean, I know I can draw the picture of what's happening in the sun, but I'm not sure the processes of fusion. I know that radioactive decay is through the weak interaction, which is a quantum process. So, we would not have much of the heat that's generated inside the Earth is from radioactive decay, not all of it, maybe a third of it. And that is the one of the factors that drives tectonic activity. And tectonic activity is required to have a planet with both water and land. So if you take away quantum mechanics, you can't have a planet that has both water and land. It will be all water or all land, because you take away that kind of radioactive decay. Let's see. What was your question? Now I've lost. Yeah. So
Or just other examples of the
right. So
importance of
the
quantum mechanics.
molecule one I gave you is actually a feature of quantum mechanics that I didn't discuss. It's called the Pauli exclusion principle. It's that every particle has these things called quantum numbers that describe it, and within an atom, no two electrons can have the same exact quantum numbers. There are four quantum numbers that describe the orbits of an electron. And so the reason that you have electrons that as you add electrons to an atom, they keep getting farther away and more complex is because of this quantum mechanical principle called the Pauli exclusion principle. And if it wasn't there, then all the electrons would just bunch up near the center as close as they could get to the nucleus. And that's why you could only form diatomic atoms. So that's a feature of quantum mechanics that's necessary for life, which again, there's features of quantum mechanics I didn't mention. That one's called the Pauli exclusion principle.
So picking up on his question about fusion, though, it seems like what CERN is doing is awfully close to the idea of fusion, because isn't it really colliding nuclei to get fusion?
Yeah, but in fusion, when they collide, they stick together. That doesn't happen with us. So to make fusion happen, you have to be building bigger atoms or bigger nuclei from smaller ones. We don't do that. That is by definition what fusion is.
And okay, and so and they can't really bounce off of each other.
Yeah,
That is
they have to fuse to form larger nuclei.
right.
Yeah.
Yeah. Okay. Thank you.
Back again here. At least initially, when the boson was discovered, the what's it called?
Higgs boson?
Yeah, the Higgs boson. I know it was referenced as a God particle, but I don't really know why. And you seems like you're the guy to ask that.
Yeah, so yeah, in the public realm, it is known as the God particle. There's not a single physicist who will call it the God particle. So the way that came about was there was a Nobel Prize winner named Leon Letterman. So we were originally building a super collider in Texas back in the 1980s and 1990s. And Leon Letterman wrote a book on why we were building the super collider. And one of the major motivations was to find the Higgs boson. In fact, the reason it was discovered at CERN is because when CERN realized that we weren't building our super collider, they said, well, we're going to make one so we can find the Higgs boson. So don't get me started on that. I'm still angry that the US shut down that machine before they completed it. But nevertheless, so Leon Letterman wrote a book about searching for the Higgs boson. And as a marketing tool, his publisher said, you need to name the book something with a catchy title like the God particle. So it was named the God particle in order to sell books. So the name the God particle is a marketing tool to sell books about searching for the Higgs boson. Yeah.
Okay, I have a question about the cost of CERN. It's astronomical, and so how did the people who came up with the money for CERN, what are they searching for that would justify in their minds all the money they put into it?
Yeah. So the CERN is funded by many different countries who want to use the data and work there, and so they sign international contracts. And a lot of positive things come out of CERN. So the goal of CERN for us as scientists is just to understand the universe. But you can argue whether that is justifiable financially. But other things come out of CERN. So my office in CERN is in floor, the first floor, the ground, or the floor number one. In Europe, you start in zero. So I'm in floor number one of a certain building, and on the floor below my office is actually where the World Wide Web was invented. The World Wide Web was invented so that particle physicists at CERN could share data with particle physicists at Fermilab. Do you ever use the World Wide Web? Yeah. Has it changed the whole world? Yes. And why? Because CERN invented it. So that would be worth the money right there if that was all that came out of CERN. But the other thing is, if you want to make a new product that's going to improve human life, you have to first understand the physics behind it. And so the goal of physicists is to understand the physics, and then the engineer can come and figure out how to use that. So I can't tell you what the physics we're learning now at CERN, what applications will come in 100 years from now, but I can give you examples. For instance, in the 1930s and 40s, the scientists were looking at things called semiconductors. And if you'd ask them what good were semiconductors, they'd say, we don't know. We're trying to understand how they work. Well, of course, every computer is based on a semiconductor. So the goal of the scientist is to understand nature. The goal of the engineer is to then use that to make a better product. But you can't do the latter without the former. So how much is that worth for you to have products in the future?
Oh, I have no problem with basic research. I'm just trying to understand how governments and industry who are penny pinchers would be convinced that they're going to get a return on investment.
Yeah, when you put it that way, it's because they basically sign contracts and they live up to them more or less. So many countries actually live up to the things they say. I'm not sure if the US does, but many countries do that.
Okay.
Yeah.
I want to give anyone else who hasn't asked a question a chance to ask Mike a question here. Well, I'll ask one more. That is what we've been talking about tonight. I think it's ordinary matter. So that is, my understanding, makes up what, 2.5% of mass energy of the universe?
About 4%.
4%. Okay, sorry,
Yeah.
it's inflated more. But how do we have any idea how this relates to dark matter in any way, or is that just a whole different different game here?
So again, we know that well, we don't. We know that there is something out there that we think is matter that's not made of quarks and the stuff in the periodic table. And we see its effect because it affects the stuff we do see through gravity. So when you look at all the stuff we do see and ask, can we explain the motion of this stuff and the way it interacts? The answer is no, not unless we postulate that there's matter out there that's made of something different. That's not the periodic table, basically. And we don't know what it is. We're looking for it. There are theories. A theory called supersymmetry proposes that supersymmetric particles may be the dark matter. There's lots of different ways to look for dark matter. One way is at CERN, so we're looking for it. And, it's out there. The other option is that gravity over very long distances acts differently than it does over other long distances. And so, there are very few physicists who think that's the answer to the phenomena we see. Almost everybody thinks it is this stuff called dark matter. And if dark matter is out there, we'll eventually discover it. Like I said, there's a lot of different ways to look for it.
How about, could it be a mass of Higgs bosons?
No, we know for a number of reasons that it is not any of the particles already discovered. Originally, people thought it might be the Higgs boson, but now that we've discovered the Higgs and know its properties, it doesn't fit the criteria for dark matter.
Thank you.
I know.
Michael, I particularly want to thank you for how you started this talk in relationship to science is investigating what God has done. And by the time my wife heard about 10 minutes of it, she says, we need to send us to our son who's wrestling with God's character right now. So thanks so very much.
Thank you, Ken. You know that I appreciate all the work you do.
Yeah.
Yeah, thanks. Ken's also in Oklahoma. So there you go.
Any other final questions for Mike tonight? Well, thank you, Mike. Thank you so much. It's been a wonderful evening, and really appreciate your time and expertise. And for those of you in Oklahoma, I appreciate you staying up late too, so that we can have this time together. And we really appreciate you coming and sharing this with us. And we look forward to having you back some other time if that works out for your schedule. So thank you again.
That would be great. Thank you all.
Yeah, and I just say for next month, Dr. Christine Cerrucci will be here, and she's an OBGYN physician, and we'll be talking about the very pertinent topic of gender affirming therapy, examining the evidence. What does the medical evidence actually show? And how should we understand that as we approach our colleagues, friends, and acquaintances in this important ethical and medical issue. So please join us again next month. And with that, I will say good night. And again, thank you, Mike, and thank you for all of you who have joined us on Zoom and here in person. So good night.
Good night. Bye.